So yesterday I made the connection between the term pH in pH scale with the mathematical function that, that removes the power or the exponent from the power of 10 on that concentration. And that's why it's called pH. And that's why it's lowercase p. I think that lowercase p, the way you write it that way, is really a standard calculation. It takes the exponent off of a really big or really small number. Okay, so let's continue on then with the analysis of our pH scale. And normally I would do this on the board. All right, normally I would do this on the board, and I did. But because I'm making a movie, the people that are watching the movie are going to have to see this. So I'm going to continue on with what we had going on yesterday. I believe for this particular line here where it says H3O plus, I put a 10 to the minus 7. Is that correct? Right, I had 10 to the minus 7. And then I think I did 2, did I do 2 and 0? What was the other number I did yesterday?
1 and 3.
1 and 3. So I'm going to put 3, 1, 2, 3, and just because I've got this concentration of H3O plus here, 10 to the minus 3. Excellent, good, right? And I told you how we can remove that, that power from that thing by using the log button. So we're going to write down the formulas in a moment, but if I take the negative log of 1 times 10 to the minus 7, the log function takes the exponent off. By putting a negative in front of it, it gets rid of the negative because I've multiplied it by -1, and I get 7. Okay? All right. And we'll write that down in a moment, and we will do some practice problems with it. Okay. Notice, again, we saw this yesterday. As we move towards a pH of 0, and we go from, say, 7 to 3, the concentration goes from 10 to the negative 7 to 10 to the negative 3, ultimately to a concentration of 1 mole per liter. The concentration of H3O goes up. So remember, H3O plus is that thing that makes acids acidic, and the lower the pH, the higher the concentration of the H3O plus is, and the H3O plus gets stronger. That makes good sense. You'd think if you had a strong acid, there should be lots of H3O plus around, and that's true. Let's now take a look at the other side of this. We've preliminarily talked about how to take that, that power off of it. We'll get to that in a moment. If we follow the logic of the pH scale, and let's say then I go from, say, 7, 8, 9, 10, let's go to 11 right there. The same trend will be true. What will the concentration of the H3O plus be? Yeah, 10 to the negative 11. Now let's think about what that means. At a pH of 11, I'm now on to the base side of the pH scale. That means that particular solution is considered to be basic. Yet I'm asking you to tell me the concentration of the hydronium ion, which is the thing that makes something acidic. That seems kind of backwards. If it's basic, why would the acidic thing be there? And it is. It's true. It's what is in the water. It's the way we calculate the pH scale. So we need to consider something else. What's going on? We would think something that's basic should have lots of hydroxide. And it does. It does. And so now I'm going to show you how we can explain how bases work in the pH scale. I'm going to tell you a truth about solutions that are aqueous, that happen in water. At neutral, if I now have another scale underneath the H3O plus scale, which you don't have, which you can write down then on the right-hand side of your scale that we did yesterday, put OH minus concentration, put it past the 14. Don't put it right underneath the 14, but put it out here somewhere. Actually, I think I can write out here, right? Put it out there somewhere. Let's talk about how much hydroxide is in water for the pH scale. Okay. Well, it turns out that when a solution is neutral, it doesn't mean that there's no acid or base. It means that the acid and base is equal. It's equal in concentration, which means if I have 10 to the negative 7 H3O plus, I also have 10 to the negative 7 OH minus. Think about what that means now. You have a glass of water. There's nothing in it. You dip a bit of pH paper in it or maybe a pH probe, and it reads 7. And you say, awesome, this is great. It's pure water. You drink it down. Like any glass of water you take out of the tap. What it really means is that, yes, it's neutral, but it's not that it doesn't have any H3O plus or OH minus in it. It has an equal amount in it. And that equal amount is a very small amount, 10 to the negative 7. There's not a lot of it. All right. Another truth, and I'm going to see if you can figure out the truth. As we move towards base, there should be more, and I'm going to tell you what this number is going to be, 10 to the negative 3. Now, I had to do a little bit of math there, and I'm not good at some simple math, so I struggled with that. Why did I pick 10 to the negative 3? Let me give you another hint. Way here at 14, it's going to be 10 to the 0, just like it was 10 to the 0 way over there. All right, remember 10 to the 0 equals what? 1 mole per liter. How did I get 0? How did I get negative 3? I'm counting backwards, sure, but that's not what I did. What's that? There's a reversal there. What would the concentration be here? 10 to the negative 11. 10 to the negative 11. Now, some of you might have counted backwards to get to negative 11. That's great. But look at the exponents. What do they all add up to? Yeah. They add up to 14. Negative 14, they add up to 14. Okay. That's the true statement. In water, and I'm going to talk about this on another slide, water will play the game. Remember we talked about the game yesterday where they're running into each other, blindfolded, and people crashing. In any solution that contains water, even if it's neutral, it's as if the water molecules say, I'm bored. Nobody's here to play the game. Hey, you want to play the game? Sure. So all the water molecules start running into each other. And every once in a while, one of them will give up its H. It'll become a hydroxide. The other one will become an H3O plus. And we'll always have a little bit of hydroxide and H3O plus in all solutions all the time. When an acid is added to the game, it's like it's making the game unfair, and it's adding a whole bunch of H3O pluses. As soon as the H3O plus team goes up, what happens to the hydroxide team? It goes down, and it goes down by an exact amount such that their concentrations would multiply to, what, 10 to the negative 14, or their exponents would add to negative 14. That's the way the chemistry works. Okay, that's good. That means now if we know the concentration of H3O plus, we should be able to get the concentration of OH minus. Once the numbers get a little ugly, though, it becomes a little tricky. So we'll think of a better way to do this. This, remember, was 10 to the 0, all right? Which means for H3O plus, it's 10 to the what? Again, I'm just making a parallel here. What's that? 10 to the negative 14. And I'm just going to finish my picture off. I still need one right here. What's the H3O plus going to be at 14 pH? 10 to the negative 14. Excellent. Good. Okay. So there's a relationship there. Now, when we take the negative log, we push that button on our calculator. Remember, it takes the exponent off and gets rid of the negative and creates this pH scale. There's no reason why we can't take the negative log of the OH numbers and create a new scale that is not the pH scale, which I'm going to write up here. But if I created a new scale underneath it, 7, and I did the negative log of the OH, 7, what would that scale be called? It's not the power of the H pluses. What's it the power of? What did I take the power of? The OHs, and it means we can have a scale called the POH scale. And I struggle to spell scale. POH scale. Excellent. You want to be writing this down. Now, I'm not going to get you to do this in your calculators yet. We'll do some calculations in a moment. But if I press negative log 1 times 10 to the minus 11, what do I get? The log function takes the exponent off of the 10. The negative gets rid of the negative. I would get 11. What will I get for the POH down here? I'm going to get 14. I'm going to get 3. And I'm going to get 0. What this means is, if I know the pH, I can figure out what the POH is. And if I know the POH, I can figure out what the pH is. Because what's true about the pH and the POH at every position? I don't know what opposite means. I need more detail. What's true about the pH and the POH at every point on that scale? They add to 14. They're equal to 14. So if I know one, I just have to subtract 14, and I know the other. That's good. That means now we can deal with bases, if I have OH numbers, and I can deal with acids, if I have acid numbers. I'm able to calculate the pH of anything. For some reason, we don't talk about the POH scale. I don't know why that is. It's just a mathematical scale for the OH. For some reason, the pH is the cool sibling of the acid and base family. We talk about acids. Ooh, an acid burn, right? If, you know, if there's some soap opera. Oh yeah, acid burn. Ah. Nobody ever says, no, it's not acid. I'm using base this time. You know, nobody ever does that. It would work. Bases burn just the way acids do. It's just not as cool for some reason. When we dip litmus paper or we dip pH paper into a solution, whether it's an acid or a base, we always measure the pH, even though we could measure the POH. But we need the POH in order to do the calculation. Okay. Let's write down some of our equations that we've slowly gathered here so that we can use them. You don't need to rewrite this. This is just the slide. I'm bringing everything back up here. No need to rewrite it. I am going to put a 10 to the negative 7 there for H3O plus. You don't need to rewrite it. You've got it. pH equals equation number 1. I need to take that exponent off, which is the log button, and I need to multiply it by -1. So we have the negative of the log of the H3O plus concentration. That is pH. Okay, we'll practice it in a moment with numbers other than 1 times 10 to the minus 7. We'll just use a mishmash of numbers. We'll just practice with it. Okay? All right. If I have OH information, let's say I'm talking about a base, then I will simply take the negative log of the OH minus concentration. Because this negative log thing is what the little letter P actually stands for. Negative log of whatever it is we're talking about. Notice that this says just H, and that's because it's using the Arrhenius acid H+, but we do H3O+. Okay. If I know one, I can get the other through a simple equation of pH plus POH equals 14. Now, we will never use it in that way, because let's say I have the POH, right? I'll bring that to this side, and it's going to be 14 minus POH gets me the pH. Or 14 minus the pH gets me the POH, whatever. Just subtract 14 from whatever you got, and you've got the other number. Excellent. What if I know the pH, and I want to get the number back? Let's say I had... Sorry, what if I know the pH? Yeah, let's say I had, we'll go down to 3 here again. 1, 2, 3. And I want to know what goes in that spot. Now, you guys already know. It's already on your thing. But what I have to do then is I have to make that 3 negative, and I have to put it up on a 10. So to get back this way, to get the H3O+, I need to take my 10, and I need to put that onto here, and I need to make it negative, so that's -3. Everybody kind of see how I put the exponent back up on the top, going back the other way? Now look at your calculators. Find the log button. I'm serious. Look at your, actually, I've got a digital calculator here that I'm going to bring up so I can make a video. And where is it? There it is right there. Look at, I'm all ready for making movies. Woo! Look at my calculator. It's a beautiful sharp, eh? It's a nice one. And if I look at the log, this video is for Clarissa, by the way. Clarissa's going to love it that I called her out. Here, Clarissa, this is how you use your calculator. Okay, so I'm looking for the log button. See it? There's the log button. What I'm looking for is above the log button. What do you see above the log button? A 10 to the x. Do you see 10 to the x? Then you have a slightly different calculator, and you got to find your 10 to the x. Second function, 10 to the x. So you're looking for a function that looks like this. It's got a little 10 and a little x. All right? Not EE or EXP, but 10 to the x. That button has one job. That button's job is to do the opposite of a log. The log takes the exponent off, and the second function, log, if yours is above the log, puts it back on, which means if I want to get the H3O plus concentration, all right, if I need that number and I'm told a pH of 3, then I'm going to use the 10 to the x button, and I'm going to press negative whatever the pH number is. And that will get me the number back. And when I press equals, it'll spit out a number. If the pH is 2.75, I'll go second function log, if it's above it, negative 2.35 equals, it'll spit out the number. Okay, excellent. I got to move my calculator for a moment because I can do the same the other way with OH concentration. If I want the OH concentration back, then I will use that second function, that 10 to the x, negative POH. All right. Those are the functions. Now we're just going to ask some questions and see if we can come up with the numbers. We just have to run it through our calculator. Before we do that, there is one more part of the note I want you to just write. All of those equations are on our equation sheet, right? Remember I pointed it out yesterday. All of those equations are on our equation sheet. So you don't have to memorize them, you just have to be able to use them. One last thing I want to talk about before you get going. This has to do with this idea of the game that I talked about, how water can play the game by itself. It can transfer a proton, produce a little bit of H3O+. So in all aqueous solutions, there's a balance between H3O+ and OH-. If the solution is neutral, they're the same. If the solution is acidic, there's more H3O+ than OH. And if the solution is basic, there's less H3O+ than OH. Write that down. Then we do examples. Then I give you a practice sheet. The first examples are just practice using the log button, negative log. The second examples go back the other way using the second function or the above 10 to the x. And then we'll do a couple of more complex ones where we use percent ionization like from yesterday to then eventually find a pH. And we'll do some with some bases like sodium hydroxide or barium hydroxide. So this is really an add-on to what we did yesterday, except now we're using these functions, the log button, to express them as pH numbers. Okay, in the examples, we're going to shorten up the way I've got it worded. I'm just going to, because we don't need all the information there. So before you start writing, I'm going to cross out a few things. You don't need to write this or write that. We're just going to practice the calculation. We good to go? Good to go? Good to go? Good to go? All right. So just write determine the pH. And the statement that says an acidic solution with, don't care about that. I'm just telling you that the H3O plus is 2.51 times 10 to the minus 5 moles per liter. Again, with the second one, don't worry about a solution with. Don't worry about a solution with. Now, I am going to do A with you, and then you can go ahead and do B and C. So once you're done writing A, wait for me, and then once we've got that answer, you can then go ahead and do B and C, and then I'll catch up with you guys. So I am going to write this one out. I'm going to write it out, an equation. To be honest, I don't need to see negative log of. You could just put it in a calculator and give me an answer to this stuff. Especially when we get to the grade 12, I don't need to see the function that you're using to get the number. In this case, I just want an answer. I'm going to write it out in this case, though, to show it to you. We want the pH. pH equals negative log of H3O plus. Again, I don't need to see this each time, but I'm writing it out this time so you can see it. negative log of 2.51 times 10 to the negative 5 moles per liter. And now I'm going to run it through my calculator. I'm going to bring up my fancy calculator now so Clarissa can see it. She's going to love it so much. It's going to be great. Now, before we do this calculation, just hold off for a minute. The log's a weird thing. Hard to know whether you got the right answer. But we know that the log's job is to take the exponent off of a power of 10. So if I ignore that 2.51, what if it was just 10 to the negative 5? What would the answer be? What would the answer be if I took that exponent off of there and got rid of the negative? It would be 5. So that means our pH has got to be close to 5. It's got to be a little higher than 5 or a little bit lower than 5. That tells you that if you're close or not. So again, put it in your calculator. I'm not going to get the calculator out yet. What are we looking at for an answer? 4.60. 4.60. I like it. It's in the right ballpark. It's close to 5, and that's what we expect. And because I told Clarissa I was going to show it to her on a calculator, I'll show it to her. Oh, she's going to be furious. This is awesome. What am I going to do? I'm going to go negative log, and then I'm doing 2.51, and then I'm pressing EXP or EE from our training at the beginning of the year, and then I'm going to put negative 5, and then I press equals, and I get 4.60. Look at that. It's like a real calculator. Awesome. Go ahead and do the other 2 examples. You're doing them exactly the same way because they are H3O pluses. You're going to get an answer for C that seems a little strange, and we'll talk about that in a moment when I take the rest of them up. Is anybody not getting 4.60? I will leave my microphone here so that we're not recording that. So you're going to go negative, log, and then 2.51. And then EXP. Now your EE, so second function right there. There's your E. Now you put in your negative 5. Equals. So yours is EE for times 10. Okay. Anybody else still not getting it? Okay. Go ahead. Push button. Let me see what you're doing. No, it's not subtract log. So that's clear. Your negative button right there. Negative is right there. Log 2.51. Yes, times 10. Yeah, that's your pH. Negative 5. You can put negative 5. Okay. Wait. No. You can do it for now. You're going to get a negative. And that's the weird thing, which is okay. Okay if you get a negative. All right. Put my microphone back on. Okay. Again, to be honest, pH is really we're not learning a new property or anything. We're just expressing the concentration of acid in a new way. So it's not like we're doing anything magical. It's got one number on one side and the other number on the other side. So I'm not that concerned about seeing the negative log function. Again, if you're unsure, it's got to be around 11, right? Because it's 10 to the negative 11. It's got to be around 11. So what do we have for that particular value there? What do you got? 10.4. 10.4, which means this is basic. And that's because there's a very tiny amount of H3O+. All right, what do we have here for a pH when we put that in? Yep. Negative 0.55, and many students will say, a negative pH? But I thought the pH scale went from 0 to 14. No, the pH scale can go beyond 0 and 14. It's just a mathematical function. If I have a really crazy high concentration of H3O+, something that's got a greater concentration than 1 mole per liter, because remember 1 was a pH of 0, and that's greater than 1 mole per liter, then we will have a negative pH. So negative pHs are okay. Even pHs beyond 14, super basic, are okay as well. All right, Let's now do the reverse function. Yes? No, you don't multiply it. You'd put it in like this. Oh, I got a calculator. Look at this. Clear. So I'm going to do the same thing. You don't do anything different. Negative, and then I press log. There's getting ready for my brackets. And now I'm just putting 3.57. There is no times 10 to the whatever on it. I'm just putting the same number in. Therefore, now I'm just going to press equals, and I get my negative 0.55. So just put it in after the log. It'll give you a number. All right. Let's now do some the other way. So here is the pH. I want to know what the H3O plus is. So this is now using the second function, or using the 10 to the x, and putting it back up where we got it from. Again, determine the H3O plus of the following solutions is not important. I am going to do the first one with you. I am going to write it out in great detail. And then after that, you're doing what you feel you need to do. Again, a reminder, the equations are on the equation sheet. All right? And you'll notice in this case, H3O plus 10 to the exponent negative pH. Again, I'm going to write it out. H3O plus 10 to the negative pH. And again, because I'm doing this first example, I am doing it explicitly. 10 to the negative 1.05. And I'm going to string another equal sign on the back end. I know that's not a good way to do it. I'm going to fire up my calculator and show you how to do it. Now I want that 10 to the x. You might have a calculator that it might be above one of the number signs, depends on your calculator. Mine is above the log. It's because it does the opposite to what the log does. I'm going to go second function, log. There it says 10 to the exponent. Now I'm just going to put negative, not minus, but negative, and then 1.05, 1.05. So I put it in just the way it looks. Equals, it turns it into a decimal number. It's not in scientific notation, but it doesn't matter. That's what the answer is right there. My answer then is 0.0891. Let's keep 3 significant digits. Moles per liter. Because now it's a concentration. All right. All you got to do is find that 10 to the x button, and then you put it in at the top. Go ahead and do B and C. Is anybody not getting those answers out of their calculators or struggling to find the 10 to the x button? Yep. Do you want me to bring the microphone to the world computer question? Not that. So that's your E or EXP button. It's the one that yours is at 10 to the blank. See how it's above the log? So it's exactly what I was showing you. It's a second function or a shift log. There it is. And then you just put it in. Yours is going to be above the log button. Yours is a 10 to the x, 10 to the blank. It's casting. See above here at the 10 to the blank? See above it? So you're doing a second function. You're doing a shift log. There it is. There you go. There you go. Let's see what's Casio. Mr. Petrus, see that you guys are straight. I'll be seeing. Me and Mr. Petrus are going to the Leafs game this weekend. So we're gonna. I'll tell them how Casio is from. Oh. So many Casio. I like so many Casio. Huh? Oh. Pittsburgh. Yep. Yep, there it is. Yep. So yours, you've got it on a ticket notation. You've got to change that. Right? So you've got it on a stage. See all those extra zeros in there? You gotta get rid of that stick. And set up. We'll set up one. Arrow down. For what one? Do it again. Oh. Okay, what am I getting for H3O plus concentration? there's lots of examples to do. This is just the beginning. What am I getting here for a number? What do you got?
Well, I got 2.69 times 10 to the power negative.
-7?
What do you got?
Yep, -7. That's good. That's good. Nothing wrong with that. That's good. Because remember, we're putting the exponent back on. Moles per liter. It's a concentration. Put the units. What do we get for H3O plus here? H3O plus. What do you got?
2.63 times 10 to the power 13.
-13. Again, moles per liter, you can put capital M for mole there. It means the same thing. And again, we're putting the exponent back up. That makes good sense. Okay, so we've now done the two ways. If I want the pH, negative log. If I want the H3O plus, back up the other way. Now let's deal with some more trickier ones here. What if we're dealing with a base? So again, you don't need to write all of this stuff. Determine the pOH and the pH of the following. And again, don't care if it's a base solution or a solution with or a solution with. Again, I'm going to do the first calculation with you, and then you can do the rest. So get down to writing to where A is, and I will guide you. So in this case, I have an OH concentration, which means I can't get a pH, but what can I get? I get a pOH, and I get it the exact same way as I got the pH. It's the same function, negative log of whatever that number is. pOH equals negative log of, I'm even going to make this shorter, 1.45 times 10 to the -4, just like I did before. And I'm not even going to show Clarissa how to do that on a calculator. Not happening. It's the same thing. What do we get for a pOH?
3.83.
3.83. It's got to be close to 4, 3.83. Now, pH plus that equals 14. So to get pH, we simply take the answer that we have, pOH, minus 14. Now, your button probably has an answer button. Can you find the answer button on your calculator? On this calculator here, the answer button is right down here. It's a green, which means I have to click alpha and then answer. So if I did this calculation, negative log, looks like I'm going to show Clarissa how to do it, 1.45 exp negative 4 equals, there's the answer I just wrote down. Now I'm going to go 14 minus, I'm going to use the answer function, and I'm going to press equals, and I'm going to have the pH. 14 minus whatever that answer was, and I've got the pH. All right. So 14. Oh, I did that backwards. I've got pOH minus 14. It's 14 minus answer equals. 14 minus pOH answer equals. And I can't remember what the number was. 10.16. 10.1, 10.16, 10.2. I like that. All right. When you're dealing with a base, you've got to do 14 minus answer equals at the end to turn it into a pH. Why? Because for some reason pH is cooler than pOH. And we like to think in terms of pH. Go ahead and find the pOH and then pH of the rest. And that's how you deal with a base. First you get a pOH, then you do 14 minus whatever that is, and then you turn it into a pH. we're going to get an answer that's a little goofy down at the bottom. Again, because I've got a really high concentration of OH minus. So it's going to bring in some negatives and going to change some of our numbers, but that's okay. Because it's just math. The same way to estimate is true. The POH has to be close to 12 for B. And then again, 14 minus, it's got to be close to 2 for pH. Does somebody have some numbers? Somebody other than Julia, what do you got? Say, I want B first, but we'll do C. Does somebody got numbers? What do you got? Somebody other than Julia, what do you got?
I have
11.6, that's good. It's close to 12. 11.6. So what's the pH? 2.4. Beautiful. This is an acidic solution. There's not very much OH in it. What do we have for POH and pH for C?
Got the POH, but the pH is 14.8.
Ah, so the pH is 14.8. Let's give you the POH first. I'll know that number first. What do you got?
-0.81.
-0.81.
Oh, 82.
82. And that's okay.
I have it.
82. So again, it's because this is a big number, and 14 minus a negative number is like plus, right? So that's 14.82. 14.82. 14.82. A pH greater than 14, yeah, that's a really crazy strong base. It can have that. Okay. Now, all that we did there was so that we could answer questions that involved some real solutions. So I've got a few more examples to do right away. We're chugging along. So this is going to be a review of yesterday's questions. But now we're going to want to find the pH. And you're writing the whole question down. This is just like yesterday's question, and we're going to write it. Yep. Yes. You can. So we've got that percent ionization. It's asking for the pH, but what it really is asking for is the H3O plus. If I know the H3O plus, oh, I don't have my mic on. I'm going to sound weird. If I'm looking for the pH, I need the H3O plus so I can take the negative log of it. So, percent ionization. And again, I encourage you guys, you should be thinking ahead. You guys all stare at me, wait for me to write something down. You have this equation from yesterday. It's on your equation sheet. That is H3O plus over the concentration of acid times 100. pH is equivalent to H3O plus. It's just we have to negative log it. So when it's asking for a pH, I need H3O plus first. Substitute your information in and solve for H3O plus. I am not going to do that with you today. And then take the negative log of the answer you get. So we have the percent ionization, 1.5. We're looking for H3O plus. The concentration is also 1.5. I bring that up to that side. I bring down the 100. I get a number for H3O plus. That's going to be in the calculator's brain. Negative log answer equals, spits out a pH. Yeah, if you could learn how to use that answer key, it makes your life a little easier. Does somebody have an H3O plus concentration? Emma, did you get a number? What do you got? 0.0225 moles per liter. If that's in the calculator, you press negative log answer equals. What'd you get? Did you do the pH? Oh, we want the pH. Again, I don't need to see it. If you really want to write it down, you can, but I really don't care. What is the pH of that solution? Yeah, what do you got? 1.64. So an acetic acid solution that is 1.5% ionized should have a pH of 1.64. All right. I'm going to get picky and choosy. I know number 3 I don't want to do. Let me just take a look at number 2. I'm going to do that one. I'm not going to do number 3, and I will do number 5. So we'll do 2 more. Number 2. Yep. Yep. Whatever you get for that is negative log. So you get pH. Okay? All right. So this is asking for the percent ionization. I know the concentration of the acid. I could write out that percent ionization equation, H3O plus over the concentration of the acid times 100. So I know the concentration of the acid, I know the bottom. Where am I going to get the H3O plus from? Where am I going to get the H3O plus? What can I... Nope, that's the concentration of the acid, so nope, I'm not getting it from that. What's that? The pH. The pH is the H3O plus. If we think about it, if I have H3O plus, I can turn it into a pH with a negative log, or I can turn the pH back into an H3O plus with a 10 to the x. So I'm going to go back this time. So it means first, before I do that, I need H3O plus from the pH. So I'm using the function to go back the other way. 10 to the negative 1.32. That's not that tiny of a number. It'll likely give you a 0 point something, something, something. What's it giving you? What are we getting out of this? Sarah, what do you got?
0.0479.
Yep, that's good. 479 moles per liter. Technically, it's a molarity. 0.0479 moles per liter over 0.05 moles per liter times 100. What percentage of this thing ionized? 95.7? 95.7% ionized. Okay, let's do one in. I will be done and I will give you the worksheet. So again, pH and H3O plus are the same thing. Just have to use a function on your calculator to turn one into the other or back, depending on what you're given. All right, and I've got two of them with a base. I'm going to do the slightly harder one where the base has two OHs in it, but that's not a problem. We can handle it. So my last example, I'm going to jump straight to 5. Negative. Negative. The order matters. Just giving you a heads up, this test is much shorter, obviously. We only got about 4 lessons worth of it on it. The written part starts with these types of calculations. I give you a concentration, tell me the pH, tell me the pOH. I give you a percent ionization, tell me the pH. Next week, Wednesday. But these are the types of calculations, and then some titration calculations, which are like stoichiometry. So it's a shorter test. But these are the types of things that we've got numbers with. 0.055 molar barium hydroxide. How many hydroxides are in a barium hydroxide? That formula is incorrect. There's 2, right? Because barium is in group 2. And that's why this is the trickier one. If it was sodium hydroxide, I'd be done. So what do I have to do to get the concentration of OHs? I want to separate out the OHs. I did this yesterday as a little practice run. Yep. Yeah. There are 2 OHs in each barium hydroxide. Somebody asked me yesterday, why do I write it that way? I write it that way because I think of it like canceling out common factors. If I write the fact that there's 2 OHs in each barium hydroxide, I can say, look it, now I'm not worried about barium hydroxides anymore. They cancel away like a common factor. And now I just have hydroxides. .055 times 2 is what? 0.11? 11? That's moles per liter of OH minus. All right, now I'm back to the problem I was doing a minute ago. From OH concentration, what can I get? What can I calculate? I get the pOH, then I subtract from 14, and I'm done the problem. So I've got the OH concentration. I'm going to get a pOH. That's a terrible written pOH because I almost wrote it as a pH. I'm not going to write it down. Negative log, blah, 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 blah. 14 minus, blah, 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 blah. Gives you the pH. What do you got, Riley? You got pH? 12.04. Do we like it? Other supporters on that? Could you tell me what the pH is too? I don't know how to subtract that from 14. What did you get? Or did you even write it down? Oh, what's the pOH number then? 1.95. Do we like those numbers? We don't like them? We don't like them? Somebody shaking their head? Negative log 0.11. 0.95. Okay, let's check it out. I'm going to get in the game now. Here we go. Negative log 0.11. Ooh, 0.95. Oh, so close. Extra 1. 0.95. 14 minus, answer equals 13.04. All right. Okay. I am done. I'm just going to stop this recorder and I'll hand out paper.